Professor Diego Córdoba from the Instituto de Matemáticas Pura in Madrid. And today Professor Córdoba is going to talk about interface dynamics for incompressible fluids, splash and splat singularities.
Thank you. And first, I would like to thank the organizers and the committee for this invitation. It's a privilege to give a talk at ICM. Okay, yes, so the topic of this lecture is to show some special singularities that happens on an interface that moves with an incompressible fluid. There are two types. One is called the splash and the other one is splat. The splash is when the interface self-intersects at a single point, and a splat is when it self-intersects along an arc. So the collaborators, my main collaborators in the results that I'm going to mention in this talk are Angel Castro, Charles Pfefferman, Francisco Gancedo, and Javier Gomez Serrano, where we proved that for one fluid and for Euler equations and Navier-Stokes equations, there are finite time splash singularities. And we also proved that in the case of Euler equations, there are splat singularities. Then, in collaboration with my former student, Tania Pernas, we showed that for a viscous fluid, you can have splash singularities, but you cannot have splat singularities. And at the end of the talk, I will present some new results on what happens when you have two fluids. And this is a joint work with Alberto Enciso and Nastasia Grubich. Okay, so in order to describe the dynamics of a fluid, we first have to set the domain in which the fluid evolves. This domain is going to be in dimension 2 or dimension 3. And then we will denote the function rho of xt to be the density of the fluid. U, the vector u, will be the velocity of the fluid, and the function p will determine the pressure in the fluid. This set of unknowns will satisfy Navier-Stokes in the case of the presence of viscosity, or when we consider no frictions between the molecules, viscosity 0, then we will have Euler equations. This, the first set of equations comes from Newton's second law, so we have force equal to mass times acceleration, density multiplied by the acceleration. This is the derivative along trajectories of the velocity, also known as the material derivative. And then the force will be given by minus the gradient of the pressure. If we have a viscous fluid, it's given by a constant V times the Laplacian of U, and then we will have some external force. For this talk, the external force is going to be given by gravity. Our fluid is going to be incompressible, divergence of the velocity equal to 0, and then we have conservation of mass. Well, these equations are nonlinear, that's clear, and they are non-local equations, and that's due to the pressure. So let me simplify things, and I'm going to take a homogeneous fluid, so the density is going to be constant, and Sasha already gave a clear description of the well-posedness for this type of equations, but let me be brief. So if we consider a domain, let's say, in the plane or in the space, in R2, R3, or a periodic setting, or a fixed smooth domain, then the problem, this system of equations, are locally well posed for a suitable space X. And let's take finite energy solutions. And what does it mean that is well posed? That given an initial data in this space, there is a solution to the Euler equations or Navier-Stokes equations for a short time that the solution remains in the same space. And now the question is, can we continue the solution for all time? Or does it generate singularities in finite time? In the case of dimension 2, it's well known that the system gives global in time solutions, but in dimension 3, this is a big open problem, even for viscosity, with the presence of viscosity. Okay, so let's do the following experiment. This is, everybody can do this at home. Let's open the faucet with water. The water, if you open and close, the water sticks to the faucet. If you open a little bit more, when the water passes a certain critical mass, then it starts moving. And this is what we will see, that the drop of water will start going down, there will be a neck forming, and at a certain time, the neck breaks down. Okay? These photos are taken by a paper in Science by Shi, Brenner, and Nagel. And as we can see here, it's clear that singularities may happen. And in this case, they happen at the boundary. Another example is when you look at the waves in the sea. You can have a wave, a wave that is a graph, then suddenly the wave becomes a non-graph, and then the wave collapses. Okay? That's another type of singularities. So let's try to model this scenario. Let's take a density rho equal to 1. We're going to try to make our life as simple as possible. So let's take dimension 2. We are going to have the fluid, and outside the fluid, in the case of the drop, there's air, but let's take vacuum to be in a vacuum region. That means the pressure, we're going to take it to be equal to 0. There's the boundary of the fluid, and then the unknowns are going to be the velocity, the pressure, and the interface itself. In this context, we can consider 3 scenarios. And a scenario in which the interface divides the plane in 2 and is asymptotically flat at -infinity and at infinity. We can consider the case where the interface is periodic, or we can also consider the case of a closed contour. Okay? I will call these 2 to be water waves, and this one I will call it to be a drop. So, since we're going to make our life as simple as possible, I get rid of the viscosity, and we are going to use Euler equations, and we have our external force to be gravity pointing down. Our fluid, inside the fluid, is going to be divergent free. And since we don't have viscosity and we are in dimension 2, I'm going to take velocities that are irrotational. Okay? And that's going to be preserved in time. Now, at the boundary, since we're in vacuum, the pressure is going to be equal to 0. One could also consider surface tension. So the pressure at the boundary will be proportional to the curvature of the interface times surface tension coefficient. And also, the boundary will move with the velocity of the fluid. So, in this setting, the goal is to write a system of equations that depends only in terms, in quantities that are defined in the boundary. That's the goal for the moment. Since in order to do that, and we are taking fluid to be incompressible inside the fluid, we are going to extend our solution, our velocity field, to the plane. How to do that is by taking the curl of the velocity to be a delta distribution, whose measure is supported at the interface. Okay? Inside the fluid, our fluid is incompressible and it's irrotational. So we can define a potential and a stream function such that the velocity is the gradient of the potential and the velocity is the gradient perpendicular of the stream function. These two functions are harmonic functions and they're conjugate harmonic functions. So one can recover one from the other by going to the boundary. By elementary potential theory, one can write down the potential, the stream function, and the velocity in terms of the measure of the vorticity and the interface, z. This in fluid is called Biot-Savart law. So we have an expression of the velocity inside the fluid once we know the measure of the vorticity and we know the interface z. Okay? So now that we know the velocity, we want to know how the boundary moves. So we have to compute the velocity at the boundary. We take limits of this expression of the velocity, and we have an expression of the velocity at the boundary that is this integral operator, which is this one, Birkhoff-Roth integral, and a term that is in the tangential direction. There's a tangential component of the curve, see? So then we have already an evolution equation for the dynamics of the curve z, for the interface, which will be Birkhoff-Roth, and we can add any term in the tangential direction which will not change the shape of the interface, and it will just be a reparameterization of the curve. Okay? So we have some freedom there to choose C. But so far, I only have used the fact that it's divergent free and it's irrotational. We have to use Euler equations. We need to get another extra equation that relates the measure of the vorticity with the curve. So we go to Euler equations. Since U can be written as the gradient of the potential, we can integrate Euler equations and we get what is known as Bernoulli's equation. This is saying that the velocity, if I know the amplitude of vorticity, I know the interface, then I know the potential, I know the velocity, so therefore I know what is the pressure inside the fluid. Okay? But what do I'm imposing at the boundary that the pressure is equal to 0. So I take the limits as we go to the boundary. And that gives me an extra equation in terms of omega and z. So these are the equations for water waves or for a drop. Okay? And remember, the c is something we can choose. It's just a way of reparameterizing the curve. And BR is Birkhoff-Roth integral. Okay, so first thing we can do is to linearize this system to see what is the structure. And we perturb a flat interface. So we're going to take a z that has this structure. And we're going to perturb 0, the measure of vorticity 0. Okay? When we plug this in the previous equations, we divide by epsilon, we take the limit as epsilon goes to 0, we pick up an equation for small f and small h of this form, where capital H is the Hilbert transform. And small g is the gravity. If we take the derivative with respect to time of f, then we get the wave equation. Lambda is the square root of the Laplacian. It's the fractional wave equation. Okay? So g plays a very important role. If in the Fourier side, that can be seen in the Fourier side, if g is negative, that means our fluid is below and gravity is pointing up, then the problem is unstable. But if g is positive, the equation is stable. And also, this system has an energy associated, which relates the derivatives of f with the fractional derivatives of h. And this is energy is conserved. Okay? So so there's a quantity, this known as the Rayleigh-Taylor condition, that plays the role of gravity. Okay? This condition is that minus the gradient of the pressure evaluated at the boundary in the normal direction has to have a distinguished sign. This actually is true. If you take the divergence of Euler equations, then you see that the pressure is a subharmonic function. The pressure is zero at the boundary, and by Hopf's lemma and the fact that gravity is pointing down, we can show that the Rayleigh-Taylor has a distinguished sign. Okay? This happens for waterways, but if you have a closed interface, then it's not required that you can take gravity equal to zero. And the Rayleigh-Taylor is still satisfied. Okay. So the problem was C.U. Wu, the first one to prove that this system is locally well-posed for, let's say, an interface in a solveless space. Let's take k bigger or equal to 4, and a measure of the vorticity in hk minus 1. Also, this f is the chord-arc condition, so if the curve does not self-intersect initially, and the Rayleigh-Taylor has the correct sign, then you have solutions for a short time in these same spaces. So here is a brief description why this works, is that one can write down an energy associated to the system, and this energy has these 5 terms, where the ones in red are the ones that are equivalent, that plays the same role that in the linear case, okay? Where instead of gravity, we have the Rayleigh-Taylor, we have the higher order terms of the interface, and phi is phi involves the measure of the vorticity in a fractional, and we're taking a fractional derivative. This was introduced by Ambrose and Mahmoudi, motivated by the work of Bill Ho and Lower. In the nonlinear case, this energy is not preserved in time, but what one can prove is this actually you get a priori estimates on this energy, and this is enough to give you a short time existence. Okay, so after the work of C.U. Wu, there has been a lot of fundamental works on the subject. For example, proving this theorem not in 2 dimensions, but in 3 dimensions, including rotation. If the fluid rotates, then you have also local existence. Or if you add surface tension, also local existence. Or if you change the boundary conditions, if you add a bottom on the sea, and then this problem is well posed. There's different proofs, and there's also an improvement of the space in which you prove local existence by obtaining lower regularity. And the latest one, due to C.U. Wu, and that is that she proved local existence for an initial data where there is a corner, where the interface has a corner. And she calls this an angle crest, and this actually initial solution maintains this corner for a short time. Now, this regarding local existence results, but there has been also work in proving global existence for small initial data in the case of asymptotically flattened at infinity interface, taking advantage of the dispersive property of water waves. And in the case of 3 dimensions, this was done independently by C.U. Wu and by Germain, Mahmoudi, and Chatat, and in 2 dimensions by Ionescu, Pusateri, and Alazar Delort, and there's several works after this on the same problem. Okay, so now that the problem is well posed and we have a system of equations, that depends only on the boundary. And let's do numerics. So these are numerics in the periodic setting by Javier Gomez Serrano. So at first, he gave an initial data, an interface, and a measure of the vorticity, and he found many examples in which the waves move, but nothing interesting happens. Then he found two very interesting scenarios. One is this one. There's a symmetry, and this wave is smooth, but as it goes down, this tip is going down, it squeezes. And then at some point, the numerical simulation cannot continue. Okay? And it seems like in finite time, the interface is squeezing the fluid, forming a cusp. Okay? And for this second scenario, I have a more interesting video. Video 1, please. Video 1. Thank you. Okay, so here's the wave. It's a graph, and then suddenly it stops being a graph. The fluid is below. And then, okay. Okay, so this is a completely different scenario than the previous one. Why? Bueno, because when it's self-intersecting, it's forming a cusp, but in between these two, there's no fluid. So you're not actually squeezing any fluid. Okay? Okay, so the rest of the talk, I'm going to talk about these two types of singularities. So for the first one, Javi, when he performed these numerics, the rate in which the wave was going down, collapsing to the other wave, was indicating clearly that it was going to collapse in finite time. One could say, okay, but you have water below, and they don't see each other. And then, if they don't see each other, there's no fluid inside, they should collapse. But the equations are non-local. Okay? So, it makes sense, but one has to prove it. Okay? So, and he observed that the curvature at the tip, when it was going down, was growing, but it was not growing fast. It was not showing a rate in which it was producing a singularity in finite time. So Javi performed more examples. Video 2, please. So you have a graph. This is a zoom in a certain region of the fluid. It stops being a graph. And then the interface seems to collapse in finite time, and we call that the splash. Okay? And the observation is that the smoothness of the curve is preserved in time. Okay, once we discovered this, then we thought there was a theorem behind. So the features of this is that we start with a graph, it becomes a non-graph, that's what we call a turnover, and then after a turnover, we have a splash. And the theorems we are able to prove is that, first of all, there is a turnover. There exist water waves that are graphs that in finite times becomes a non-graph. And the second theorem says there exists initial data where the chord-arc condition is satisfied and it's smooth, the interface, which collapse in a splash, preserving the smoothness of the curve. But Javi's numerics is telling us that it goes all the way, does the two things at the same time, I mean, one after the other, for the same initial data. Turnover, splash. So we would like to prove that this too happens consequently. And for that, we prove that nearby Javi's solution, which is a numerical solution, there's an actual solution of water waves. But of course, it's a stability for a short time. Okay, so the idea of the proof for the turnover end up being a very simple proof. It's actually, one just have to cook up an initial data that has a vertical slope at 0, for example, and the rest is a graph. So the derivative of the first component of z vanishes at one point, and at the rest of the points, the derivative has let's say, a positive sign. And one has to cook up, the interface is given, one has to cook up a vorticity such that makes at time 0, this is the first component of the velocity, to be at 0, to be negative. And that will force that when you go forward in time, this first derivative of C1 will be negative. So the change of signs of the first component of the curve will tell you that you have a non-graph. That if you go forward in time, but if you go backwards in time, you get the opposite. Your derivative with respect to alpha of the first component of C1 will become strictly positive. Then you have a graph. And since this is a local existence result, you can go forward and backwards in time. Yeah. What about the splash? Well, the splash, we are going to take advantage that Euler equations are irreversible in time. Okay? So the goal is to start a local existence theorem starting from the splash. And then choose an initial data that separates the point of the splash. If we manage to do that, then we can go backwards in time and have a singularity. What is the problem? The Courtart condition fails, and the theorem we have in local existence require the Courtart condition to be satisfied. And at that point, the measure of the vorticity is not well defined. Okay? So actually, what in this scenario, what blows up is the L infinity norm of the measure of the vorticity. But the curve is smooth, and the normal component of the velocity is well defined. So let's apply a conformal map that opens up the splash. For example, by taking the square root, and the branch of the square root is going to be here in the middle, and it will cross this point, splash point. So when you apply the conformal map, what you're doing, you're opening up the splash. And now in this new domain, your interface is smooth, and the Courtart condition is satisfied. Of course, in this new domain, we have different equations. But the potential and the stream function are harmonic functions. So therefore, the transformation to this, I'm going to call tilde domain, is well defined, and what you pick up is a stream function, a tilde stream function, and a potential stream function, which are harmonic as well. And they are conjugate harmonics. So now we can define a velocity field in the fluid by taking, for example, the gradient of the potential. And once we have the velocity field defined inside the fluid, then we can, it's going to be rotational, so we can do the same strategy than before. We can extend our solution to the plane by imposing that the vorticity is a delta distribution whose measure is supported in this C tilde. Now, the system of equations in the tilde domain has this other structure, okay? And the goal is to prove local existence for this new system of equations, but now our curve does satisfy the Córdoba condition, and omega, the measure of the vorticity in the tilde domain, is well defined. We cook up an energy associated to the system. Now we have to include these other terms over here, which are the zeros of the conformal map. We have to make sure that the zeros of the conformal map are outside the fluid, because when we get the solution, we want to invert this operator and go back to the real world and say that we have a real solution. And in order to do that, they have to guarantee that those zeros remain in the vacant region. So this will guarantee that those points remain in the vacant region. Okay, so with this energy, again, there's these two terms that have the same role that in the linear case. And when you take derivative in time of this energy, these components will all be bounded by powers of the energy. That's no problem. And the ones that will pick up higher order terms are this one and this one. And the higher order terms are exactly S. So you can control all the quantities by the energy, and this one, which has 4 derivatives on phi, and phi is like the measure of the vorticity. And this escapes from our energy. But if you take the derivative in respect to time to the fractional derivative of phi, you pick a minus s, and those cancel out. Okay? And one can prove that the problem is well posed. You have local existence in the tilde domain. Okay, now take a splash in the tilde domain and take your initial data, the normal component of the velocity, to point away from the branch. So for a short time, you have a solution. And since you chose initially that your velocity is pointing outwards, then you can guarantee that your interface has moved away from the branch. That means in the real world that your splash has opened. Okay? Well, if you add surface tension to this problem, it does not prevent a splash forming. Splat is, instead of that intersects on a point, it intersects on a curve. Well, one can apply the same proof and prove local existence from the splat. Choose a velocity field that takes you away from the branch for all the points on the branch, and you can prove local existence. For a splat, we never saw this in a numerical simulation. Okay? But this came out just by the proof of the splash. And also, if you add rotation to the problem, and this is due to Kutan and Scholar, you can prove that a splash and splat singularity forms. We would like to prove that you start with a graph and you end up in a splash. And I'm going to tell you a strategy how to prove this. Well, we use the stability theorem, and what we want to prove is that starting in Javi's solution is a numerical solution that starts from a splash, and as you go further in time, it goes away from the splash, and then it becomes a graph. If one can guarantee from the stability theorem that your solution from Euler equation, your real solution, actually remains as close as you want to Javi's solution, then you win. Of course, if you do this in the real world, you're not going to be able to control the constants of the stability theorem because the measure of the vorticity blows up. So one has to do this in the tilde domain. In the tilde domain, to go from a splash to a graph, it's just that, that the interface moves a little bit farther away from the branch, and it becomes a graph in the real world. Okay? Okay, so in order to compute how close Javi's solution is actually to a real solution, this requires to obtain rigorous bounds on thousands of terms, and a computer can do that, and interval arithmetics is a tool that gives you rigorous bounds, but it will take a lot of time and energy. Okay? Okay, so what about viscous fluids? So in the case of a viscous fluid now, is the strategy does not work because the equations are not reversible in time. An example is when you put a viscous fluid in a porous media. Now instead of being governed by Navier-Stokes equation, will be governed by Darcy's law. This is a system of equations that can be written the same way I wrote water waves. There's a Rayleigh-Taylor associated to it. The Rayleigh-Taylor will take care of the higher order terms. And in that situation, we prove the existence of splash singularities. But the case of splash singularities, those do not happen when you have a viscous fluid in a porous media. For Navier-Stokes, the splash singularity can be also proved, and the absence of splash singularities, this is an open problem. So the strategy for the Navier-Stokes or for the porous media equation is again to apply this conformal map that opens the splash. In this tilde domain, one proves that the system is well posed, but now we have a parabolic system, okay? And we cannot go backwards in time. But we prove a stability in the tilde domain, and then you choose, in the case of Navier-Stokes, you can choose a measure of the vorticity initially that forces you to cross the branch. And if you manage to do that, you have you have in the tilde domain an interface of splashes that the velocity is taken such that it crosses the branch, and then anything close by will cross as well. That means that in the real world, you have, by a perturbation argument, you have a splash for this type of viscous fluids. In the case of the incompressible porous media, known as also as Muscat, one cannot actually once you give the interface, the velocity, the normal component of the velocity at the interface is given. And surprisingly, if you have a splash, any splash, the interface, the velocity will force you to cross the branch. So nature is telling you, forcing you to have a splash. Why don't we have a splat singularity? Well, the proof goes this way. We make, again, the transformation in the tilde domain, and we prove that if you start with something in sobre space, it becomes real analytic instantly. And actually, we can measure how the strip of analyticity grows. And it grows at least linearly in time. Okay? So you start something in HK, it becomes instantly real analytic. Once you have a width of the strip of analyticity, you want to study how the strip of analyticity decays. And if you choose, and what we can show is that the strip of analyticity does not grow faster than one exponential. Does not decay, sorry, faster than one exponential. So as long as the curve remains smooth and the Chord-Arco condition is satisfied. So we assume there is a splat in the tilde domain, the Chord-Arco condition is satisfied, and the smoothness is one of our assumptions. Therefore, if it reaches a splat, it has to be real analytic. Now you go to the real world, and by analytic continuation, that's impossible. It cannot self-intercept along an arc. Okay? Okay, so I have 5 minutes for the squeeze. Okay, so now, what happens if, can it collapse when we have fluid inside? Okay? We are squeezing the fluid. So this is what the numerics show us, but actually we can have a drop like this. This is the experiment, right? Here we cannot use the trick of opening up the splash, because if we do that, we are not going to be able to go back. We can solve the equations in the tilde domain, but we're not going to be able to come back because the zeros of this conformal map will be inside the fluid. So we have to have a different strategy. So what happened, let's take the case in which we have two fluids with different densities, two different densities. And for this scenario, we need, in order to have a well-posed problem, we need that the difference of the pressure, we need a surface tension, okay? And let's say both are irrotational and the interface moves with the fluid, the usual conditions. In this scenario, Pfefferman, a few years ago, Pfefferman, Ionescu, and Victor Lee, they show that a splash singularity cannot happen with two fluids. A smooth splash singularity cannot happen with two fluids. The proof goes like this. Again, your vorticity is a delta distribution. And let's take the interface to have 4 derivatives. And we assume some regularity on the velocity field. So that means on the measure of the vorticity. In those conditions, then the measure of the vorticity satisfies a variant of Burger's equation. So the vorticity is going to be transported in time, so it cannot blow up. Okay? And if it cannot blow up, you cannot have a splash with those conditions. And that is shown here, where they compute the evolution of the Khordad condition. This is the Khordad constant, and they get this bound. That the Khordad condition is bounded by a double exponential, as long as the vorticity remains bounded. So in order to have a splash, or the smoothness of the curve has to be low, or the vorticity has to blow up, or both. So what we prove recently is that for two fluids, there exists a stationary splash singularity. So let's say we have a fluid here with a fixed density rho sub 2. Then there exists a perturbation. We're taking a small density outwards and small gravity as well. This is not true for large gravity. And there exists a surface tension coefficient in which a stationary splash singularity happens. The regularity of the interface is C2 alpha, and the vorticity, the measure of vorticity is C alpha, for alpha between 0 and 1/2. Now, the proof consists of applying the implicit function theorem to some known water wave solutions that have a splash singularity. Crapper computed some specific water waves known as Crapper solutions. These solutions need surface tensions and they don't have gravity. And what we show is that on that family of Crapper, there exists a splash singularity with one fluid. By the way, Crapper solutions is only for one fluid. 2 minutes. And so Crapper solution only for one fluid. So we prove that among Crapper solutions, there is a set of stationary solutions with a Splash singularity, and among those, we perturb with an outer fluid. And we are able to prove there exist two fluids with a Splash singularity. Now here the key point is that one has to obtain estimates, one has to obtain information from the velocity, information of the measure of the vorticity from the velocity. One has to invert certain operator. To invert this operator when you have a Splash singularity is the real difficulty of this problem. And we managed to do this in a Banach space where in a space with weights, where these weights depend on the cusp of this singularity. Now that this is done, now that we understand how a scenario which has a singularity at time t equal to 0, then why don't we perturb time? And this is a work in progress. So what we hope is that with this weighted solidus spaces, we would like to prove a priori estimates starting with an initial data of this type, where you have a cusp, take the normal component of the velocity at time 0 to open up this Splash, and to have a drop of this sort. Here the regularity will be low regularity on the interface, we'll have a singularity on the vorticity, and when it opens up, the regularity, the interface smooths out, and the vorticity as well. And with this I finish. Thank you.